We have free printers on campus.
I think Trio has free printing. I don't know if you're part of Trio.
Not yet.
Yeah, you should definitely join. If not, I can print out stuff for you if you just ask.
I found for the longest time, I've been keeping the same CHEM reference sheet, and I think last year I kind of got rid of it. But I found a big one I think is going to be helpful, and I like, so I just wanted to print it out.
Yeah, you reminded me. I forgot to print out new periodic tables for people.
I could also just go over to the library.
Yeah, I just don't know if you have to pay or not, but I don't mind printing for you.
Oh, well, that makes sense. That makes sense. Are you still thinking 6,000?
All right, let's go ahead and get started. So first of all, so just another reminder, so please make sure you're registered. So is anyone not registered for all three, lab, lecture, recitation? Is everybody at least in some section? Okay, perfect. So again, just make sure you're registered, and I think you have until Monday to add and drop classes without financial penalties. So just don't forget about that in case you're thinking about adding or dropping other classes. Please don't drop chemistry. Let's see. So yeah, I think the lab's kind of self-sorted. So we had 20 people show up on Tuesday, which is perfect. So I hope to see anybody who didn't make it on Tuesday today for lab. And any other questions before we get started?
Could you remind me of the Thursday lab of permission code?
Thursday permission code is SUVV. And so that's going to be today, so 2:30 to 5:20. So giving y'all a 30-minute break between recitation and lab. And I apologize, we pack it all in, so please bring your lunches, stay fed and hydrated throughout the day. All right, anything else before we dive in? So let's finish up. So we had been going through our electron pairs on Tuesday. So now we're at electron pair 6. And so what's going to be the hybridization of electron pair 6? And again, this is just its formal name, so we're not actually invoking d orbitals. sp3d2, perfect. And so we have 6 electron pairs, so that means we should have 6 orbitals formally combining. Again, that's not what's actually going on, but for our bookkeeping, that just now tells us the pretty picture that it's going to be making. And so let's pull up our chapter 9 pretty picture for reference. So sp3d2, and so giving us these 6 little hybrid lobe orbitals. So again, they are actually p-base orbitals. You can kind of see that. So px or pz, px, py. So those look just like p orbitals, and so that is what is going on. And look, so it gives us that nice octahedral shape. And so, can anybody think of what the classic example of AX6 would be? So 6 substituents. Yeah.
Sodium. Hang on, actually. Sorry, it's been. It is sulfur hexachloride.
Sulfur hexachloride. Perfect. So you could pick hexachloride. I was kind of thinking hexafluoride just because this is the one that people breathe in. So you can breathe in sulfur hexafluoride, and then it would lower your voice since the air is less or more dense, excuse me, than our regular air. But you can see sulfur hexachloride works as well, so you can kind of tell this would work for any of our group 6 plus a substituent. They all follow that same pattern. And so now I'll draw it. So sulfur, do chlorine, because why not? And then don't forget your lone pairs. And then, so in the center, they're going to be kind of square planar. And I'm just using the wedge to show that the chlorine's coming out of the plane of the board. So this chlorine's also coming out of the plane of the board, behind the plane of the board, and behind the plane of the board. And don't forget your lone pairs. And so let's look, so what's our total electron count on sulfur?
48. Oh,
think that's total electrons in the system.
8.
And then, oh, so look at that again. So remember, how many is it feeling?
6. Sorry.
So it has 6 bonds. 12, yes. So 12 total electrons that sulfur is feeling. So yes, it's hypervalent, but that's okay. It's on our 3rd row, and that just means it's large enough to accept all those electrons. So again, not invoking d orbitals. I'm going to keep emphasizing that because so many textbooks are wrong when they say that. I don't know why they do that oversimplification. And then what's our geometry? Check your chart. Parent shape.
Octahedral.
Yep, octahedral. And so this is, right, our fully symmetric. And so now let's look at the next one in that group. And so looking at something that would be square pyramidal or pyramidal. So that would be AX5E. And so I'll give you the classic example for that. So that would be bromine pentachloride. And so this one, bromine is our central atom. So of course, bromine has 7 valence electrons. 5 of those will go into bonding with our chlorine, and that leaves 2 of those as a lone pair. And so I'll try to keep the geometry the same. So I'm keeping it with that octahedral geometry in mind, just replacing our chlorine on the z-axis with a lone pair. And I would prefer the z-axis because that gives it the most amount of space. And again, don't forget all your little lone pairs on chlorine, especially when we do our collaborative quiz today. I'll draw so we can show that, yes, the lone pair is occupying space. So it would be interesting to run some WebMO calculations and see, is this perfectly, 90 degrees here, or is there some distortion? And so if you haven't had lab today, you'll kind of see what I mean. When you run the WebMO, it gives us kind of a better picture. And again, these are kind of just our back of the envelope calculations, and then we can use our WebMO or other computational chemistry software to give us an even more refined picture. And so what's the geometry again of this one? So square pyramidal. And then another term that I think I failed to bring up yesterday, but it just came to mind today, is sometimes you'll see this other term called electron geometry. So this would just be like its molecular geometry is the shape. And then electron geometry, if you ever see this, it's basically asking, well, what parent family is it from? So in this case, right, it's from the octahedral. And so you're looking at the position that the electron occupies. So you could say that this has an octahedral electron geometry. And again, it's just what parent group is it part of? That's kind of its big family electron geometry. And then we look at where the actual atoms are to give us the geometry, or if you saw this more specified, the molecular geometry. And so now let's look at our next kind of example in this family. So AX4E2. And can anyone think of what might be the classic example for this one? Any guesses? Yeah, nice. So xenon tetrafluoride, is the classic example. And so xenon has 8 valence electrons. 4 of them will go into bonding. And so that probably means that the other 2 will be hanging out as lone pairs. So those would be on the z-axis. And then our fluorines will be occupying kind of the center. And so you could draw this in several different ways. So I was trying to emphasize that our lone pairs are along the up and down z-axis here. And this is all, the fluorines are all coming in and out of the board in a plane. So this is square planar. Sorry, I gave away the geometry. I just want to emphasize that, yes, it is flat in the plane. So you could also kind of draw it, like so that you can emphasize more that, yes, this is all flat in a plane. And then you can kind of draw your lone pairs. So either way, and so we'll do our geometry, which I gave away as square planar. And so what's the electron geometry? Octahedral, perfect. And then remind us again, what's the hybridization? sp3d2, perfect. So we're still in our electron group 6. And so now for the last 2, I don't have any examples of these. So bonus points if you can find molecules that would fall under this weird T-shaped pattern that we would expect. So with 3 substituents and 3 lone pairs, and then same with this linear, again, theoretical geometry, where you have 2 substituents and 4 lone pairs. So if you bring me an example of either one of these, then I'll give you some bonus points. All right, any questions about this overall? And so again, I might write here, so write your hybridization to remind yourself. sp3d, so all the electron pair 5s are all sp3d. All these are sp3d2. And then maybe this is where we go back and remind ourselves of the electron geometry. So of course for the 2-1, it doesn't really matter. It's still going to be linear. I'll just put E geometry linear. So for 3 electron pairs, write your electron geometry is all going to fall under trigonal planar. And so what's the parent electron geometry for 4 electron pairs? Tetrahedral, perfect. So all these, right, have our parent tetrahedral electron geometry. We saw that with ammonia and the trigonal pyramidal, how we just replace a substituent with a lone pair. Same thing with water, still in that tetrahedral parent geometry. And then what's our parent electron geometry for group 5? Trigonal, what's the second part? You can read that, trigonal, bipyramidal. And so again, all those, the sawhorse, the T-shaped, and our linear all, again, have that parent electron geometry. So is that starting to kind of make sense, falling into place? And again, I'll pull up this chart again. And so you can see our parent electron geometry is really reflected too in our hybridization. I don't know why this is having issues loading. All right, excellent. So let's move on to isomers then. And so let's kind of draw the distinction. So we have isomers. So isomers are just different, either spatial or connectivity with the same formula. And there was a good question asked in lab. It was kind of like, well, what's the difference between isomers and resonance? And let's just review that. And so remember with resonance, and this is really will help you if you go on to OCHEM too. So resonance, right, when we're looking at resonance structures, all we're doing is we're not breaking any single bonds. You just think of it as a movement of electrons. So in this case, if we wanted to show resonance, we make our new double bond and then move those electrons to the other oxygen. And so that's resonance, right? So we didn't break anything, we didn't change the connectivity, we didn't change the order of anything. But now isomers, we could change things. So you can pop things off, you can change either the 3D arrangement that we'll look at, or just change the connectivity entirely. And so the example from your book that it gives is propanol versus isopropanol. So propanol would be your straight chain alkane. And so breaking down the nomenclature of this organic molecule, so you have prop, which stands for 3 carbons. So we have our 3 carbons. The ol group means the alcohol, so there's our alcohol group. And so propanol, again, is just our straight chain. And then if you look at isopropanol, so iso stands for this specific group here, where you have a carbon in the middle of 2 other carbons like that. So this would be an iso group. And so we have isopropanol, and then we see, again, now our alcohol is attached to that central atom to give us isopropanol. So isopropanol, that's your rubbing alcohol. So we can also look at other isomers for fun. And so hexane, this is an organic solvent, actually safety warning. So this is, I don't know if I've mentioned it. Have I talked about hexane in this class before? All right, so this is my public service announcement. So most people don't realize how toxic hexane is. So hexane, at least the straight chain alkane version. So hexane has 6 carbons, so hex is for 6. So the most common form is this 6 chain, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, making sure I count my carbons. So this is hexane in kind of the abbreviated form. You could also draw it out explicitly. Sorry, I can't count. But the thing about hexane, and why people don't really realize how toxic it is so once it gets metabolized by your body, it turns into something that is just the right length to go between your synapses. And so this wouldn't happen to you if you were just exposed to a little bit of hexane. But the problem is a chronic exposure over time, because you'll find that people recommend using hexanes to clean up oil spills, for example, in industry. So you have a huge pile of oil, and people will say, yeah, just throw some hexanes on it and clean it up. It's very effective at cleaning up oil, but if you don't want to breathe in hexanes for a long period of time, so eventually that could lead to, neurological issues. So you would have like motor function issues, and since it starts messing with your synapses. So don't expose yourself to hexane. And again, that's a huge safety thing for yourself, because again, people use it a lot still, especially in industry, and they just don't realize the hazards. So don't get yourself long-term exposure to hexane. So pentane and heptane, because they are either 5 or 7 carbons, they are perfectly safer, so they're not gonna be the right length to bridge between your synapses. Yeah.
Is that the same as like that white powder that you put on like your driveway for an oil spill?
No, hexane would be like a solvent. I'm not sure what powder.
Just like spill powder you buy at the store.
Yeah, I mean, sometimes I would have to look at what the powder is like, because sometimes it could just be like an absorbent, like Sealite or something. And, but yeah, I'd have to look into what you're actually talking about. But then let's draw some isomers for hexane. So you could draw different connectivity. So we could do, let's see, 1, 2, 3, 4, 5, and then 6. So you could have something like that. So that has 1, 2, 3, 4, 5, 6 carbons. And then we could tally it up if you don't believe me, so we could see that the formula is the same. So let me draw it out explicitly again. One, 2, 3, 4, 5, 6. Always count your carbons. That's my biggest piece of advice if you move on to organic chemistry, is count your carbons and then count again. And so now you can tell why organic chemists like the shorthand version, since it took me forever. And so you can see they have the same formula, so you can count up the hydrogens: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then counting, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So they both have that formula, C6H14. So again, that's what makes them structural isomers. And you could continue having fun with this, so drawing more isomers. So you could also, so notice I put the methyl group on this carbon. So of course, if I put it here, those are the same. So they're the same by rotation. But I could have put it on the middle one. And so now that's a different isomer. We could go 1, 2, 3, 4. Make some more isomers. So 5, 6. Probably missing some isomers. Oh. 1, 2, 3, so 1, 2, 3, 4, so you could put it there as well. And so again, you kind of get the picture. Let's just prove that this one has the same formula, so carbon, and now we have to draw out all our hydrogens. So remember, each point here is a carbon, and none of the hydrogens are ever drawn explicitly unless it's attached to an alcohol. So make sure we have 6 carbons, 1, 2, 3, 4, 5, 6, and then count up your hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, sorry, I miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and I forgot to write 14 right there. So I almost left carbon without its hydrogen. So again, same formula, still an isomer. So we also have other stereoisomers, and so we'll look at today enantiomers. And so this is just a non-superimposable mirror image. And so I'll pass these around. I'll also draw them out. Oops. If I could get them. What do I do? No, I can't orient them properly. There we go. So I'll hold them, the camera. I'll pass them around. I'll draw them out. Go ahead and pass them around, and you can try to rotate so you can't break anything yet, because that's the only way to change them. And so let's draw what it looks like as those go around. And so so the easiest way to kind of draw enantiomers is if they're non-superimposable mirror images, you can kind of pretend that there's a mirror plane here. And then you can draw them. And so I'll just put X. So it doesn't matter what it is as long as it's 4 different substituents attached. X, Y, Y. So this is in the plane. Now this is coming out of the plane. So out of the plane. Behind the plane. So that's what it looks like drawn. And then if you could kind of imagine rotating the right image in your mind, you would see that it is not superimposable. So if you kind of redraw so that the Y is at the same orientation there. And that's where the molecule kits are super helpful, because this is difficult to do in your brain, especially if you're doing it for the first time. And so again, my other advice is if you go on to take OCHEM is buy molecule kits and use them. They are very helpful. Don't be too proud and think that you can visualize everything in your head. And so you're rotating this. And so that means when you rotate it, the Z would be pointing behind. And then W goes in front with the rotation. And then you can see, okay, yeah, they're non-superimposable. And the other way to think about it is, of course, your hands are also enantiomers, so they're mirror images, and you can't superimpose them, right? They're not the same. You can't rotate. So that is an enantiomer. And so this, let's define this. So this carbon here, where it has 4 different things attached to it, would be called a chiral center. And so anytime you have a carbon in any molecule, so again, this is more when you're looking at like organic chemistry, you'll look at all these crazy molecules. Then if you find a carbon with 4 different things attached to it, that's going to be a chiral center. And so now we want to ask, well, why do we even care about these chiral centers? And so this is probably the most famous example of enantiomers gone wrong. And so this is, I think it's an anti-nausea medication. So it was used for pregnant women to try to mitigate their side effects. And so the problem is, so you can see, so thalidomide has a chiral center. So there's your chiral center, the carbon right there. So the hydrogen is not drawn, but that's the 4th thing that's attached to it. And then these rings, since the ring is not symmetric, so you notice one side of the ring has this double bond oxygen and nitrogen, the other ring doesn't have anything. So that makes it as 2 separate things attached to it. So there we can identify our chiral center. And so the R and the S just tell you which way is which, but that's again more for OCHEM. And so yeah, it was, you can read the Wikipedia. So basically it was prescribed for morning sickness. And then what they found is, oops, actually one of the enantiomers leads to bad side effects in babies. And they didn't realize this. And also, once you take thalidomide in your body, it makes a racemic mixture. So even if they were to manufacture the non-toxic version, it gets metabolized in your body. It makes both of the racemic mixtures, and either way, you still end up with those bad side effects. So that's really something to think about, especially in drug development. You have to test that. Can you make either a clean racemic mixture Like, can you get it to be 1 enantiomer or not? Does it matter? And so sometimes that's an issue with potency too with medications, that 1 enantiomer is non-active, the other one is. And then of course trying to determine too, and this is, why studies are very important, because then you have to understand, well, how is it actually metabolized in your body? There we go. So it says S-thalidomide is a bioactive form, but then it can racemize, so basically it can change chiral centers. And so it kind of goes through the process. So that's why we care. And so another note, and why chirality is important. If I can find the page, give me 1 second. So I couldn't access the actual paper on this computer. I would have to jump on to my other credentials, but let me post the paper. And so the paper that I was looking at, but you could look at this topic if you're interested in it, or if you wanted to even write your research paper about it. And so what they did is they were trying to just figure out, well, how did life emerge? And so not to go down like a whole philosophical discussion, you can talk about this in your free time more, but basically, some of the questions of the origin of life is, okay, if we started from a primordial soup, how do we go from achiral to chiral? And so that's part of the question. And the other thing is, so life has a certain handedness. And so the question is, well, how did one mixture come out if you have, again, 2 racemic possibilities? And so some of the theories for that, and so this is kind of the case study that I stole it from. And so basically it's, again, how do we go from our primordial soup to a single enantiomer? So all your amino acids, goes back to the handedness of life. They're going to be L enantiomers, so they have a certain chirality, and so we're not a racemic mixture. However, we would expect achiral reactants to give us a racemic mixture of both enantiomers. And so again, there's question, how did this happen? And so this paper, what's kind of interesting about it is they tried to do a simulation of how this might happen with selective crystallization. And so you can see, again, all these amino acids, they have handedness. This is a chiral center here. Again, hydrogen not drawn, but it's there. And so what they did is they added a base to kind of mimic, maybe there was some sort of condition that allowed this to be deprotonated. And so that would break the chirality and then allows you to form the other enantiomers. You use a base, deprotonate it, then that creates an achiral molecule, then you reprotonate it, and then you can form the other configuration. And so they kind of proposed that maybe in the primordial atmosphere that there was selective crystallization. So there's this phenomenon too known as Oswald ripening. And so basically it starts saying, like, if one starts making crystals and then it starts coming out of solution. So let's say you have, again, your racemic mixture like this, but let's say the L starts crystallizing out, so it starts coming out of solution, and then that's going to cause more L to want to crystallize on top of that. And so maybe eventually they all went to L because of that, because again, starting with racemic, selective crystallization, and maybe you make 1 enantiomer. Again, that's one guess, and so you can look into this more if you're interested, but it's something to think about, chirality, since we are, again, there's handedness to life. So let me post that, and I'll post these notes after today's lecture so you can look at that for yourself if you're interested. All right, so let's look at other types of isomers that you'll see. And so now this is looking at our octahedral geometry. And so this is, so we have our cis, so cis isomer, so this is kind of where they're next to each other, same side. And then this is going to be our trans isomer, where they're opposite sides, so notice our chlorines are on opposite. And so this is when we just have two different substituents and then four other fluorines here. So this would be AX2, Y4. And so anything with this general form can have two potential isomers. You can also have, in organic chemistry, cis and trans as well. So you could do like chlorine, for example, on one side. So this would be cis, again, same side, versus a trans isomer where your chlorines are on opposite sides like that. So probably won't see this too much in this class, but again, if you go on to OChem, you'll see a lot of cis and trans isomers. And then so with the square planar geometry, we can also have cis and trans isomers. So here we have cis platinum, where we have, again, the chlorines kind of on the same side, versus the trans, where the chlorines are across from each other. And the last type of isomer, and I'll have some models for this one, and let me draw them again too. This is a funny drawing. So we have the FAC isomer, and FAC, so the way I'm holding it, it's called FAC because it's like facial, they're all in one face, and we can redraw it in case you can't tell. And so sometimes people draw these, the octahedral a different way, so kind of more oriented like this, or we can, I'll just do some generic molecules. So we have X, and then this is coming out of the plane of the board, X, like that, and then Y, Y, Y. So this is, again, the FAC. If you wanted to draw it in the other orientation, that's kind of more what we're used to. So you could draw it like this. So and once I'm done drawing these, I'll pass these around. So X, X. So you can see, right, we just kind of flopped it over. And so sometimes if you don't see the term FAC, this is also known as cis-cis isomer. I've seen this in certain textbooks. So again, you have two cis, so on the same side. And so that's compared to the mer isomer, which they're on like a T. And now I'll draw it down here. So I'll send these around now. Oops, and I'll drop my pen. And so the mer isomer is probably easiest to draw in our usual orientation. A. So XX. And this one is called the trans-cis isomer. And so you can see probably why that is. Oops, sorry, let me draw this a little better. So you can tell, right, these two X's, one of them is trans, the other is cis to each other. And so that's why you'll see that other name of trans-cis. And let me finish filling in the rest. Y, Y, Y. So that's your mer isomer. Okay, any questions on isomers or anything? And hopefully the WebML/lab assignment kind of help with that. And again, if you haven't done that, you'll play with it this afternoon. All right, we ready for hybridization? So let's look at some hybridization, and let's do a little warm-up with CO. So go ahead and draw the Lewis dot structure for CO, and then start thinking about, well, what's the hybridization of my carbon and my oxygen? How do we get a triple bond? Or is it a triple bond? What's going on there? How are our CO drawings going? Okay. So how many total electrons do we have in the system?
12.
Is it 12? Yeah, I think it's 10 electrons, so 4 plus 6. And then how many bonds do we get between them? So 3, and those are the structures I saw. And then does carbon have a lone pair? And what about oxygen? All right, perfect. So now let's start analyzing the structure. So now we can go back and determine, well, how do we make this triple bond? And so what's the hybridization of carbon then? It's got a little lone pair. So SP. And so, right, we can start thinking about, so carbon, and it's SP hybridized. So we can tell, right, the lone pair is occupying one of those hybridized SP orbitals. And then, so let's see what's going on with the other one. And then what about oxygen? What looks like it's hybridization? Or SP as well, yeah. So yes, it would be SP as well. And so again, now we'll kind of draw this. Oxygen, so we have SP. Again, that lone pair is going to be in that other SP hybridized orbital. And so now right away we can tell, well, here's where we get our sigma bond from, right? So they're facing each other, those two sp orbitals, so that means they're direct. And so that gives us a sigma bond. All right, so now we've accounted for one of these little lines. But then what about the other bonds? What orbitals are coming together? What orbitals do we even have left? So the S was mixed for both of them. Yeah, so Py and Px. Exactly. And so we can draw that out. Let's see if this doesn't get too messy. So, right, we still have, so, right, our PZ, that's the one, again, formally, we're saying that Z is going to be the highest principal rotation axis. And so PZ combined. But then, yeah, that leaves us with PX and PY. And so I'll formally call PX up and down. And so we have PX, and they're available on both of them. Maybe I should have redrawn this. Oh my goodness, sorry. Okay. Hopefully this doesn't get too nasty. So we have our PYs, so those are in phase with each other. And so what type of bond can you have with our PYs? Or PXs, sorry, I switched the axis. Our PX, so what kind of bond? What's that? It's like through space interaction. Covered it Tuesday briefly. Yeah, pi bond. And so, right, we have this through space interaction, so they're in phase. So there's one pi bond. Yeah, and then, so then there'll be another, because we have our PY available, and so I'll make a new drawing, since now it's starting to get convoluted. And so let me just redraw. So, right, we have our SP. There's our bonding orbitals. And so we still have, I'm just going to draw PY here now. So PY is coming in and out of the plane of the board. So coming at us. I apologize, I don't have better drawing skills. Wow, that looks even worse. And so again, right, you have this through space interaction, so your PY orbitals are both coming out like this, so in phase we can have another pi bond. Yeah, like a pi. Yeah. And so again, that's our through space. And so now we've accounted for all three of those bonds here. So now we can tell where they came from, right? So again, just to re-emphasize, so that means we have one sigma bond and two pi bonds. And again, we saw that from the sp-sp orbital interaction of carbon and oxygen. So those came together. Again, direct interaction. So anytime your lobes are facing each other directly, that's a sigma bond. And then the pi bond is anytime you have those p orbitals like that, and then you have that through space interaction. So let's look at another example. So let's look at acetone. So take a few minutes and try to figure out what kind of bonds we have. Yeah, question?
I just want to ask why the, like, PX is being the up and down axis and then PY is, like, going diagonally?
So you have Z like this with CO, And Z is just usually the principal rotation axis. Now Y and Z, you could switch. So I just, for my sanity, I usually do X up and down, and then Y is usually coming out of the plane of the board. But if you formally called like this one Y and this one X, it doesn't matter.
Okay.
Yeah, and even you could swap the axis, like Z doesn't have to be the principal rotation, it's just by convention it normally is. So yeah, I won't penalize you if you were to, swap them, yeah. You can always redraw your coordinate system in any way.
So, could I have an SP bonded to a P orbital?
Potentially, but. Here, so I see a lot of blank pages right now. So let's just start with, so the first thing is you want to determine the hybridization. And so looking at our carbon here, what do we think the hybridization is? And so remember, you're just looking, like, how many things is it attached to? But how many things is it attached to? So it's only attached to 3 things, right? And so that means if we have 3 things, we're only going to mix 3 orbitals. So what's the hybridization?
SP2.
So SP2. And then I'm going to go ahead and start kind of redrawing that. Like, okay, so we know what our SP2 orbital looks like. I'll pull up this handy picture again. So, okay, SP2. And this also tells us, right, the geometry, because we also want to be able to know, well, what does acetone look like, in the 3D shape? Is it flat? Is it, not flat? And so we can tell, well, SP2, that means that carbon center is planar. And then you can kind of draw your lobes. Like, well, has to look something like that, right? Our SP2 hybridized lobe. And so what's the hybridization on this carbon, either one of these methyls? So how many things is this central carbon attached to?
3.
Oh, recount. So it's attached to 3 hydrogens and then 1 carbon, right? So it's attached to 4 things total. So what does that make its hybridization? So sp3. And so we know, right, these are probably going to be tetrahedral. And so now I probably can't draw this. There we go. So carbon. So we could tell, right, we have one sp3 orbital. It's in line with that sp2, so that's going to make our sigma bond right there. And then these other ones are going to just be bound to hydrogen. And so hydrogen, right, just has a s orbital. And so they're just bound. So of course these are all formally sigma bonds. And again, we can tell that this has a tetrahedral geometry at this carbon. So same thing with our other side. So that's just symmetric. Bound to our hydrogens. All right, so now let's look at what's going on between the carbon and the oxygen. And I purposely left off the lone pairs, but how many lone pairs should be on oxygen? So 2 sets of lone pairs. And so now that kind of makes it more obvious. So how many things is it attached to, including lone pairs? So 3 exactly. And then so if it's attached to 3 things, what's the hybridization on oxygen? sp2. And so now we see where our other lobe is going to come in. And so we have oxygen. We can tell the lone pairs are then occupying those 2 of the sp2 hybridized orbitals. And then the other one is involved in our sigma bond. All right, so what's left? How do we get this double bond? What orbitals do we have left for bonding? Yeah, so we don't know which one. We could formally say one or the other. What are you feeling, Y or X right now? Any preference?
Y.
We'll go Y. And so we have our, we'll say again PYs. We're not quite sure, but we'll call them PY. And so they're both available, right? Because we had sp2, so 2 p orbitals went into there, but then we have our py that was not hybridized, so it's available for bonding. Same thing with that carbon, and so that's what gives us that double bond then, is our pi bond from that py bond.
So one of the bonds is a sigma bond and one of the bonds is a pi bond.
Yeah.
Is
And
that true for all of the bonds?
Probably, yeah, like 99% of the time. I can't think of any exceptions, but yes. So anytime you see these bonds in, then you're thinking like we saw for the triple bond, then it was a pi bond, or excuse me, 1 sigma, 2 pi. Here it's going to be a sigma and a pi. And so yes, so usually, right, you'll have the sigma bond first, and then the double bond is a pi or something. Let's look at kind of other cases. And so now you can see why we have these substances. So we have substances that are called aromatics. And so one classic example of that is benzene. And what this means when you have an aromatic system is it just means you have a delocalized pi system. And so we draw out benzene. So benzene shorthand, actually there's several different ways to draw it. So sometimes you just see this, which really emphasizes the delocalization, but what that really is, it's alternating double and single bonds. But then you could draw, note, a resonance structure. So again, resonance structure, we're just moving around electrons, so we're not changing the overall connectivity, but you can draw it and move the double bonds. And so they can move round and round. And again, that's all it means by aromatic. And so let's look at the orbitals on this. And let me also draw it out explicitly so you know what the heck is going on. And so benzene is, again, just 6 carbons in a ring. And so they have alternating single and double bonds. And so that means each carbon has 1 hydrogen attached to it. And so the next question would be, well, what's the geometry? What does benzene look like? And so looking at our carbons, so what's our hybridization on these carbons? So they all have the same.
3.
So it's attached to 3 things. And so what does that mean when it's attached to 3 things? So sp2, so we know that all these carbons then are sp2. So that helps us. So you can think about like looking down, top view, right? These are all sp2 hybridized. Oops, I apologize. Did not leave myself enough space. Right, so you can see the hydrogens too are also in the sp2, so that's all planar. And so now we can tell right away that this is a planar molecule. So sp2. That's right, all sp2. And then, so how do we get these double bonds, or how do we get a delocalized pi system? So what orbital is left? So py, we'll go with py. And so then we can draw out all the py's. So that means that all these carbons have py's that are available for bonding. And so again, what you get with this aromatic system is it's totally delocalized, and you have the electrons essentially running around. Yeah.
I'm just not getting it. Why is the PYs available?
So when you have the sp2, that just means that we put in an s plus 2 p's. And, oops. And so we, put in maybe pz, px. You could call it pz if that, so it doesn't matter what p orbital you call it. It's just that only 2 went in, right? And so you remember from last quarter, every molecule has their s and their 3 p orbitals available. And so now we're saying, well, these 3 went in to the sp2, and that left whichever this one is. Again, we're formally just calling it py. You could call it px, pz. We just went with py, but basically this is empty. It's not involved in bonding right now, so right, these all combine to make the bonding scenarios. This one is currently empty, but then available for that pi bonding. And so that's what you get, is this, again, delocalized pi system, so those electrons can just circle around that benzene ring. And then, so let's look at some examples. I won't belabor this too long, because we should touch on polarity a bit more. But if you go into CHEM, there's a lot of weird, funky scenarios with nitrogen, and it may not seem completely obvious, but if you break it down with these orbitals, then we can kind of figure out what the issue is. And so if we look at the issue, so let's just look at this example. And so by our method, right, we just kind of see how many things is it attached to. And while looking at it, right, nitrogen is attached to 1 carbon, 2 hydrogens, and 1 lone pair. So that's why they have here kind of our expected hybridization is sp3. But then if we really want to examine it, we have to kind of figure out maybe what's more energetically favorable. And so now let's kind of analyze this in depth. Redraw this, oops. We have our carbon, NH2 here. And so let's say that, let's just pretend for a second that it is our expected sp3 and what that looks like. And so as we try to draw this, so what's the hybridization on this carbon again? I think I heard someone whisper it. sp2. So this is sp2. And so now, right, we're just thinking of our orbitals. So we have carbon. It's sp2, right, doing its thing with oxygen. And so if we try to match it up with this NH3, and we just went with its expected kind of sp3 geometry, so nitrogen, 1 in bonding. Then we have this like just lone pair kind of dangling over here, so this would be bonded to hydrogen, hydrogen. So it's okay, but actually what we find is better. So right, this is currently just non-bonding hanging out. What's actually more energetically favorable is if nitrogen was sp2, then this could be delocalized across, and that is more favorable. And that gives you some resonance. And so that's what actually happens, and this is reflected by the actual geometry. And so we find actually, so we're going to redraw carbon. So carbon's still sp2 like we expect. And now, so of course carbon has this empty, so this is supposed to be going up and down. So this is in the plane. So it has our empty, we'll call it py orbital that's available. So this is just empty, essentially available for bonding. And now if we make that nitrogen sp2 instead, that puts those hydrogens, so now they're planar. So now all this is planar, and then the lone pair can actually go into the up and down py orbital. And so now our little lone pair is in there, so that's where our lone pair is. And then we can, again, spread that across and make some sort of pi bond. So you could draw then some resonance structures. So you could put this right over there, move the electrons up. And that's more reflective of the actual nature then. And so again, this is better because you can do pi bonding and delocalization. So better, you have those pi interactions now. Whereas before, where if it was in this sp3 hybridized like we might just think that it would be, you know, just counting, we find that, well, it can't bond with the py then. So does that kind of make sense? And so this is more like higher level stuff anyways, but I wanted to introduce it now because I swear in OChem they might not cover it as well, and it's good to kind of look at it now and kind of see why that is and really analyze our structures. And so I'll leave this here so you can look at other cases, why it's funny, and you can look at it for yourself. But it's anywhere where you can have kind of, you know, start drawing some resonance structures. You can kind of see, well, you know, maybe I'd want to draw a double bond in, but then if you want to draw a double bond, your orbitals have to be appropriately there. Yeah.
Is that represented with the NH2 together instead of having the H's split off in a, like a Lewis dot representation? Is it just because it's a group that it's represented like that?
Oh, I think it's just like shorthanded. Just, yeah, that's kind of, I guess, the drawback of sometimes just these quick little sketches is they don't really show you like how are the hydrogens, what is the geometry, and that's why it's kind of up to you to figure out the geometry. All right, so let's talk a little bit about polarity and look at some more examples. Let's go to a new page. So remember, for polarity, you're kind of looking for unevenness. And what I always reference kind of this chart. So if you look at whatever electron pair you're in, always the fully symmetric is going to be your first one, right? Where they're all kind of going out evenly in every direction. And so what we mean by that, so let's say we're looking at PCl5. So PCl5, we could draw. And so to determine polarity, what you can do to kind of help you is draw these arrows. And so for the chemistry convention, I like to draw it like that. So where you have the little plus sign arrow tail is kind of towards your more positive side. The arrow is pointing towards the electrons. I think physics has the opposite convention. But if we were to draw this out, so draw all our arrows, so we find, well, they're all going out evenly in all directions. And so again, it belongs to this parent geometry. So that means as long as it's going out evenly in all directions, that's going to make that nonpolar. And then what if we looked at ClF3? So take a minute, look at that. Do you think it'd be polar, nonpolar? So what do we think for this one? Polar, nonpolar? Drawing it out. What about these lone pairs, though? So you have some sort of unevenness, right? So you have your fluorines kind of going out in different directions. And then also our lone pairs. So this would be polar. So now they don't all cancel out, right? And then again, you have kind of one side with lone pairs, other side with not. So that would make this molecule polar. Bless you. So what about, let's look at dichloromethane. So polar, nonpolar. So what do we think? Polar, nonpolar? Nonpolar? So right, we have these chlorines, so those are going to be pretty electronegative. And so again, we kind of have this unevenness. And so I would say this is polar, right, versus, so you could do carbon tetrachloride for comparison. And so carbon tetrachloride, so now each one of those bonds is individually polar, but since it's going out in all directions evenly, that makes it nonpolar. So what about ammonia? Polar, nonpolar? Would you say polar? So polar, exactly. So these are pretty nonpolar, but then we do have, right, our lone pair there. So again, unevenness, so that makes it polar.
Are there any like asymmetrical molecules that are nonpolar?
I can't think of any off the top of my head, but there could be some with like small dipole moments. And so you could always, because there's always a range too of like, well, how polar is polar? And so there are ways to quantify it, and I think on your WebMO it actually spits out a calculation that you'll see. And so another way to like quantitatively compare, so of course you could run these WebMO calculations, and then what you're looking for, if I can find it on here, oh here it is the dipole moment. So then it gives you some idea of how polar it is. So acetone obviously is pretty polar since we have a oxygen on one side, and so that makes it polar. And so you can kind of see how polar based off of this number. And so if we wanted to compare, let's just look at ether. So ethers are kind of less polar. They still have an oxygen in them, but it's kind of more in the center. Oh, come on. I have to look at this specific one. And so we look at, so this is diethyl ether. And so when people say ether, they usually mean diethyl ether. And so this one has a dipole moment, so it's a little bit less now, so 1.15. So you can kind of see, right, there's a range too of polarity. And so let's look up like acetonitrile. So acetonitrile is fairly polar, so it has a nitrogen on one side, and then this nitrogen has some lone pairs. And so that one, where's the dipole moment? I'll be annoyed if it doesn't have dipole moment on here. Oh, I don't know why it's in the text. So dipole moment of 3.92, so that is now, more polar. And so let's just look at carbon tetrachloride. I know we're almost out of time. Just so we could see. Please have a dipole moment on this page. There we go. So this has a dipole moment of 0, actually. And one more. Let's look at dichloromethane. Now I'm just having too much fun. So dichloromethane. So that's 1.6. So you can kind of see the range of dipole moments. All right, I think we'll have to end here for today. So those of you who haven't had me before, how recitation seems to work is most of the time is taken up by the quiz, unfortunately. But I encourage you to stick around, ask questions after. And then the other thing is, so I am really available this quarter for you guys. So the only other class I'm teaching is online, so that means my Monday, Wednesdays, and Fridays are pretty free. But I don't want to just sit in my office all day, but I'm available by appointment. So just send me an email. We can meet, Zoom, in person, wherever. If those times don't work for you, I can meet, nights, weekends. Just give me a heads up so I can arrange my schedule. All right, so let's go ahead and take a 10-minute break, and then we'll go back and take a quiz after our break. And I will go ahead and end this stream.